dark only really by comparison to what's around them. Those spots, of course, can be the size of Earth, sometimes even the size of Jupiter. We do solar observing here every Sunday that it's sunny in the summer outside, and I have to say last summer we saw 3 sunspots in a row. It was amazing. And then we had the same folks back the next week, and there were no sunspots. But anyways. But it's always, I think, interesting for students to realize just how big those sunspots are, and to realize that they're a lot brighter than you think. So we have a quick animation, a little thought experiment for them to think about that. That sunspot is dark, but only compared to everything else around it. And if you could somehow defy the laws of science and remove that sunspot from the sun, and bring it closer to the Earth, and cause a mass panic, what you would also see is that sunspot is about 10 times brighter than the moon reflecting sunlight. So that sunspot by itself is actually quite bright. And that can be a tricky concept sometimes for our kids, so we try to do a little hands-on experiment to show that. I've got an incandescent bulb here. It's got 60 watts, so this will be a little bright. If you don't like bright lights, you can avert your eyes. But I'll go ahead and turn this on. It's bright, but it's not nearly as bright as our 4,000 lumen projector right here. I'll go ahead and turn this off and place it in the path of our projector. And what are we going to see up on the screen? We'll see this shadow. Now typically if I turn this back on and I ask the students what we're going to see again, what do you think? We will still see, of course, the shadow. Sometimes the things will see a different color, but we'll still see the shadow. That light bulb is bright. It's not nearly as bright as our projector bulb, and still casts a shadow on the screen. So just a way to talk a little bit about sunspots and how they're dark, but only by comparison to what's around them. Sometimes we'll pull out our infrared camera again and show just how much heat is coming off of that projector too. Then we move on to some of my favorites, some of these images that are all real, that have all been captured by our eye on the sun, by the Solar Dynamics Observatory. To me, I think that's the most exciting lesson from this show, is that everything you're seeing is real. This is the promise and possibility of human ingenuity and what we put into space and how we're able to study our star. And something we take for granted, but it's really extraordinary to be able to pass that on to students and get them as excited about it. So here's Tornado Alley, which occurred a few years ago on the sun, and to let them know that each one of those solar tornadoes is bigger than the planet Earth, also in terms of scale. And then we like to make a model. This whole show is about taking these images from space and trying to make some models here on stage. So we're not going to make a solar tornado, but we are going to make a fire tornado. That's another theme with these fires. Fuel. And of course, we need 3 things for a fire: heat, fuel, and oxygen. Yeah. So we've got our fuel on those cotton balls. I'm going to go ahead and ignite that, and then we're going to spin this and get a convection current going. So we'll get a flame with a convection current. A tornado here on Earth, you have lots of dust in the wind and a convection current, and here, of course, you have magnetic energy. So on drastically different scales, but that same basic idea of spinning to make this a bigger tower. So here we go. And when we stop the spinning, the flame will go down. Should we try one more time? Let me center this. Well, I heard it. Ooh, thank you. Gotta have an ah. No, I'm just pandering. All right, we'll go ahead and put this out with our flush capacitor. Not everything here is high tech, let me tell you. All right, but just another way. Right, we start out with all the video. By the end of the show, you're getting just one through sun. All right, a few more other examples of magnetic energy on the sun that we talk about. Sunquakes. So we have this imagery from SOHO. Of course, predates the SDO, but it's one of SDO's sister satellites studying our star. Solar and Heliospheric Observatory gave us this image of sunquakes. And I like to tell the students that if we were near the sun and we had air there, we could hear the sun, we could have sound energy coming off of those ripples. Of course, thankfully there's no air between us and the sun. But what would that sound like? Well, we can measure those waves to determine what they would sound like. And scientists have actually measured waves coming from the sun, and they're too low for us to hear, but they played them back at about 4,000 times the speed to make it much faster, like hearing yourself as a chipmunk on a tape. Anyone remembers tapes? And so what I'm going to play for you now is some SOHO data that's been sped up, so it's playing back at a much higher pitch. And we'll also just take a look at a basic animation of molecules that we show our students, that sound means that it's a pressure wave. Unlike light, which can travel through space, making that distinction for kids that sound is a pressure wave pushing on air molecules. So we're seeing the pressure wave here, and that's the sound of the sun sped up. All right. Well, we'll let that roll. It's going to go back to the sunquake in a moment. And then let's make our model of how that works. So how can we look at the waves in a sunquake and interpret what kind of sound they're giving off? Well, we can measure the size of those waves, the distance between those waves, how fast they're coming. And we can do our own model here where we relate the length of a tube to the pitch of the sound that's given off inside that tube. So we're going to do a quick demonstration of that right now. Again, of course, using fire. Again, that's my thing. So what I'm going to do with each one of these tubes is put about 10 squirts of ethanol in the tube. We need heat fuel and oxygen. And we're going to cap this. Shake it up a little bit. I'm going to do the same thing in the other three tubes. And then we're going to ignite these and listen to the differences. So the only variable, other than human error for me doing this, is the length of the tube. The material is the same. We control that. The amount of ethanol, again, is going to be 10 squirts. The method with which we're capping them, the method with which we're going to ignite them is all the same. The only thing that's changed is the length. And the longer the cylinder, the longer the wavelength that will be produced when these are ignited. So I'd like to ask the students how many of them play instruments, if we have anyone in band. So they'll already know the answer. If they play a piccolo versus a trombone, for instance, which one of these tubes will give us a high-pitched sound, and which one will give us the lowest pitched sound? So I'll ask you guys right now, which one of these tubes is going to give us the highest pitched sound? The shortest one, yeah. We'll put that to the test. Okay. We'll give these a moment. Let me pop up the cell phone energy here. Okay, and we'll go ahead and ignite these. These shouldn't be as loud as some of the things we've heard before, but they will be a little loud if you don't like loud noises. This will be the last loud thing in our program today. But I'll go ahead and ignite these one at a time, and we can hear for ourselves which one is the highest pitched and which one is the lowest pitched. Here we go. That was the softest. So you can definitely hear the difference, right? Oh, thank you. So which one was the lowest pitched? It was the longest, which were particularly for elementary students. I try to make sure that we hold these horizontally so they know that we're comparing the length, because otherwise we get into sort of the confusion of height. But this is actually the lowest pitched one. And then we're able to relate this basic physics concept to the imagery that we get from the sun. Talking about all of these things, sets the stage for more dramatic displays of energy from the sun, like these real images of solar flares from the SDO. And this next one, which just takes my breath away, a CME. We love to direct our students to the sun today as a resource too, to know that NASA is always uploading current images, and you can actually see what our star looks like just simply by going online. And then we discussed geomagnetic storm impacts. In 1989, for instance, Quebec City was brought down as power grid by a solar flare. And so why do we have these satellites? We're getting lots of basic data. It's also helpful for us here on Earth because these satellites are gathering data that can be predictive tools. If we can better predict when our sun is going to be a little crankier, so to speak, then we're able to better safeguard our electrical systems, our electronics, and even occasionally airplanes, particularly ones that fly near the poles, are occasionally rerouted because of solar activity. But of course, it's not all bad. We've got the solar wind all of the time interacting with the Earth here and producing the auroras. We showed the students a lovely image of the aurora borealis in the boreal forest of Canada, exciting the gases in the air, giving off plasma, giving off those lovely colors. But what would be better than seeing an aurora in real life on Earth? Seeing an aurora from space. So this is a great place to go next. Some real imagery from space of those magnetic, almost ribbon-like dances taking place in our atmosphere, looking down from 220 miles above the Earth. And then we make a model. So that's what I'm going to do right now. I'm going to switch us over to our augmented reality system. And so what we have here, earlier we brought out these magnets. We'll often have a kid come up and we'll talk a little bit about magnetic poles, north and south, and how they attract, and north, and have them fight. And a tug of war here, but they, of course, can't get them to come apart. But then we get a little more complicated. We've got these two bar magnets here. They're actually just props. We have rare earth magnets inside here. They were a little hard for students to understand that on stage, so we designed these sort of plastic bar magnets to go over top so they can see north and south. And right now we've got red and white, north and south, attracted to each other. We'll let the students come up and play with this. We have a camera over top, and basically we've got some Arduinos inside here. So whenever I move these magnets around and I change the magnetic field, the Arduino sensor is going to send that data to the computer, and the computer is displaying this here. It will alter that in real time. So we'll see north and south move. We'll see the shapes change and also the colors. So the colors there are showing us just how intense the magnetic field is in different spots. So we can go ahead and change that in real time. In a way, acting like the sun on the Earth. And make some different shapes. This is just a fun interactive for students to come up and we'll also use this in our adventure stations. So one or two students can do this in the show, but other students can try this out throughout the day, make a few different shapes. Maybe a sliced apple or other things like that. This is an augmented reality system. It was actually developed by the Franklin Institute. If you go to Philadelphia, you can see this on display at an exhibit, as well as an augmented reality balloon blower. So it's actually showing moving airstreams, but similarly using Arduinos to show how that works. And it's an exhibit that we wanted to adapt into our roadshow, just to illustrate the science of magnetic fields and how they move, and the idea that the auroras are really nature's way of visualizing magnetic energy for us, or the end result of the sun's magnetic energy interacting with the Earth's at the poles. So in the same way we're visualizing it with computers, nature does it for us through the aurora and puts on a nice show to boot. All right. I believe that just leaves one final module, which we'll get through quickly here. That is our solar system module. Oh, that's the wrong thing. to get into some of the complexities of the magnetic energy on the sun, but we can talk a little more just about the basics of the solar system. The idea that the sun centers a neighborhood of rock, gas, and ice. What happened to Pluto and the Kuiper Belt? That's a big question that we get a lot. So actually, at that point, what we do is we line up the students. We have 8 different beach ball planets, and we line them up, and we sing the Do Re Mi song, but we have new lyrics for elementary school students to learn the planets and what they're all about. And then we showed them some examples of SDO data of some phenomena that they might have heard of, like a solar eclipse, which of course was big last year. Was anybody here for the solar eclipse? I'm just curious. How many of you guys saw totality? I am jealous. My whole staff was gone. They went to see totality. But we had a great time here. We made some sun funnels, and I'm still actually eating rice checks from all the pinhole projectors that we made. All right, so here's some data that we have from the SDO. Here's a great lunar photobomb. Just talking to students about that cosmic coincidence of our moon being about 400 times closer, but 400 times smaller from our perspective here on Earth, and what it looks like when it photobombs the sun. But it's not the only object that does that from our perspective. So since the SDO is orbiting the Earth, you might occasionally see the moon go by, but you'll also see some other planets. Oh, we've also got eye on the sun and eye on the Earth here. So we saw from our eye on the sun, but from our eye on the Earth, you can see that dark shadow from underneath the International Space Station from a solar eclipse, the shadow of the moon on the Earth. We also like to mention to the students that we have 2 other planets, and that we can occasionally capture transits of those planets across the sun with the SDO. And here's an image of the transit of Venus, which we sped up a bit for the sake of the show, but we still wanted to leave it long enough to give the kids an idea of just the size comparison of little Venus there. The size, almost the size of Earth, but trying to make its way across our star. And hopefully it will make it by the end of the show. And then that allows us to lead then sequentially into scale comparison for the students, starting off with Mercury and the other terrestrial planets, and then moving to the gas giants. Sometimes they're surprised to see how small Mars is by comparison to the Earth. Then getting to Neptune is a huge shock for them. And then finally getting to the Sun. And that's when I'll ask the students if they want to see more. Do you guys want to see more? Yes. We have one more part of this, so we're going to compare the Sun, our tiny dwarf star, to some others like Sirius A. And we'll watch our very own star disappear as we get to the red giants. There it is. They use our round of applause. Heard a little clapping for our red giants. And leading the students on the thought of where did our sun come from in the first place? That we've had these early red giants in the universe, these gigantic stars, the supernovae. They gave us these clouds of dust and dust and gas from which form solar systems like our own. So kind of in a meta way, in a very Carl Sagan way, the idea that we are star stuff, and now through tools like the Solar Dynamics Observatory, we are starting to understand our own star. And we'll end with a quick clip from Mike Hennessy. Just sort of a mission forth about the importance of STEM careers. So let's have a hand for Mike.
I always wanted to be an engineer, and I didn't know what engineers did. So engineers are actually using scientific and mathematical principles to make things. Now, who out there doesn't enjoy making things with like Legos and other toys like that, and making something new? And I remember at the Buell Planetarium making rockets and airplanes, which is really fun, and that's what engineers do. NASA really only hires the best. Do your homework, understand what it is to be an astronaut or a flight controller or a scientist for NASA, and then study towards that. And if it resonates in your heart, then you know you're on the right track. The best way to predict the future is to invent your own future today.
Solarquest, I'd like to thank you guys for your time today. We have Astronomy Weekend coming up next week, and that's something that really couldn't happen without the support of the amateur astronomers of Pittsburgh.